Let's talk about concavity. A curve is said to be concave up on an interval a to b if at each point on the interval the curve is above its tangent line at that point. If the curve is below all its tangent lines on a given interval, it is concave down on that interval. Let's just draw quickly these two scenarios. So let's say you have a function that looks like that. Its tangent lines are all below. So the tangent lines look like that. So this is concave up. And if I had a graph that looks something like that, the tangent lines are all above. And so this is considered concave down. Assume that the first and second derivatives of a function f exist. The function f is concave up on an interval I if f double prime of x is greater than 0 on I, and concave up at the point a comma f of a if f double prime of a is greater than 0. The function f is concave down on an interval I if f double prime of x is less than 0 on I, and concave down at the point a comma f of a if f double prime of a is less than 0. Example 1 says, find the intervals over which f of x is equal to x cubed minus 4x squared plus 3 is concave up and concave down. So let's go ahead and find the first derivative. That's going to be 3x squared minus 8x. And then we need to find the second derivative, and that is 6x minus 8. And if we set that equal to 0, or actually, I'm going to create an inequality and see when this is greater than 0. If we solve this inequality, if I add 8 on both sides, then we get 6x is greater than 8, and divide by 6, we get x is greater than 4/3. And similarly, if we solve the inequality 6x minus 8 is less than 0, we would end up getting x is less than 4/3. And so 4/3 is kind of like our separating point, and we would say that f is concave up on the interval 4/3 comma infinity, and f is concave down on the interval negative infinity comma 4/3. And that is our answer for example. A point x sub 0, y sub 0 on the graph of a function f is called a point of inflection, also sometimes called an inflection point, if the curve is concave up on one side of the point and concave down on the other side. The second derivative at this point, f double prime of x sub 0, will be either 0 or undefined. Example 2 says, find the points of inflection and concavity of the graph y equals x to the 4th power divided by 2 minus x cubed plus 5. The first thing that we want to do is we want to find the first derivative. So that's going to be 4 over 2x cubed minus 3x squared. And that simplifies to 2x cubed minus 3x squared. And then I'm going to go ahead and take the derivative of that. And we would get 6x squared minus 6x. And I could factor out a 6x from that and get x minus 1. And if we set that equal to 0, then we get 6x equals 0 and x minus 1 equals 0, and x equals 0 and x equals 1. And so now we can use another sign chart or sign diagram. And instead of plugging the test numbers into the first derivative, we would plug it into the second derivative. So my test numbers are going to be -1, 0.5, and 2. and we want to plug them into f double prime, or I guess in this case it'd be y double prime. So y double prime of -1, that would be 6 times -1 squared minus 6 times -1, which is 6 plus 6, so that's 12. This is positive for the second derivative, which means that it's concave up. And then y double prime of 0.5, that is equal to 6 times 0.5 squared minus 6 times 0.5. That is equal to 6 times 0.25 minus 3. And that is definitely going to be a negative number. So this is negative, and that means that it's concave down. And if we evaluate y double prime of 2, that is 6 times 2 squared minus 6 times 2. That's 6 times 4 minus 12. That's going to equal 12, which is positive. So that is concave up. So that means that we are going to have inflection points when x equals 0 and when x equals 1. And if you evaluate y of 0 and y of 1, you get 5 and 9/2 respectively. Go ahead and verify that. So your points of inflection are 0, 5 and 1, 9/2. And again, that is because at this x value and this x value, it's changing from concave up to concave down. And then from here, it's changing from concave down to concave up. So that's why we have points of inflection there, or inflection points. And then we want the concavity. So y is concave up on the intervals -infinity to 0 and 1 to infinity, and y is concave down on the interval 0 to 1. So that completes example 2.